Okay. Good morning, everyone. My name is Manuel Carpio. I'm associate professor in the Pontificia Universidad Católica de Chile. I have today a work about the influence of the urban heat island effect on interstitial condensation in residential buildings with the temperature oceanic climate in winter, the case of Puerto Montt in Chile. This work is with other professor, Guillermo, Konstantin, Andrés, that is here, and me, Manuel Carpio. Don't worry, this. Yes. Okay, this is Puerto Montt. It's a very typical German city in the south of Chile. This city is very beautiful and has the sea and the mountains very near. This is special to the climate of the area. For today, I go to talk about the context, research methodology, constructive solution, result, and conclusions. In the study, we work with two phenomena, the condensation phenomenon and the urban heat island effect. For this, the goal of this research is to analyze the influence of the effect of the urban heat island in a temperature oceanic climate with the temperature and relative humidity recorded in 4 different points of a city in the southern Chile, and its impact on the surface and interstitial condensation of the building envelope work. Okay, about the research methodology, in Chile, we have 2 different regulations about this topic. The NTM 11 about the requirement and accreditation for the environmental conditioning of building, and the Norma Chilena NCH 1973 about the hydrothermal behavior of building element and component interior surface temperature. If you see in the map, Chile is in the south of the country, in the south of the planet. No, it's very far of Santiago, the principal city. And Puerto Montt have a CBF classification in Köppen with marine climate on west coast, hot and dry summers under the influence of the ocean.
Je continue.
Yes, you can see here in the map that Puerto Montt is very near of the sea. Okay. This is the city of Puerto Montt. We installed 4 different sensor data in 4 different points of the city, and other sensor data in a rural area, very near of the airport. The sensor data are Netatmo. The sensor record data every half hour of temperature and relative humidity inside and outside the houses. Constructive solution. We simulate and calculate with 3 different constructive solutions. The solution 1 with a U-value of 1.6, a solution 2 with a U-value of 0.8, and solution 3 with a U-value of 0.3. Here you can see in the picture the different solution, and in the full paper you can see all the characteristics of the material. This is the 3 more typical solution for the city. Result. About result, we have 4 different steps: temperature and relative humidity data, temperature profiles, water vapor pressure profile in the envelope, and condensation time. And we did the study in 1 year, but for the conference, I have here the data for only 1 month, for August. August in Chile and in Puerto Montt is the coolest month. And here you can see the temperature and the humidity data for 1 month. We have three dies with more hot, no? The 5, 12, and 27, and the point more with lower temperature always is the point 1 in the city. Temperature profile in the envelope. And we did the temperature profile for the free solution for the 4 point every half hour in 1 month. We have a lot of information, but this is only one example for the solution 2 with a U value of 0.8. And we can see that always for the simulation, the internal temperature is 20 Celsius degrees. And we can see that the profile of temperature with the different materials. For the construction, we have cement, brick, cement, and the insulate. This picture, this graph, is for the day with lower temperature, only 0.4 Celsius degrees, and 96% of relative humidity. About the water vapor pressure profile in the envelope, and this is an example of the same case and we compare the saturation pressure with the partial pressure of vapor. And in this case, we can see that we have condensation in the envelope. We study this free solution in 4 point in 1 month, and we studied that for August that have 744 hours, the bad case is with the solution free, okay, that the 40% of the time the construction have condensation, and the best case is for solution 1 in the 0.4 that only 0.8%. I think that this is good, but the best case is that 0% of condensation. Now we are working with the ministry to do recommendation for envelope and that in the coolest month have a 0% of condensation. Conclusions. The effect of urban heat island cause an alteration of the microclimate in different parts of the city for certain days of the coolest month. On some occasions, it increases the temperature and relative humidity above the maximum recorded by the meteorological station, which reduces the potential for condensation. The risk of this happening is present in the same way for the study city. For future research, it is proposed to design constructive solutions adapt to urban microclimate that comply with local and international standards to deal with the influence of the effect of urban heat island in order to reduce the risk of condensation in the envelope of building. Thank you very much for your attention. Here you have my email if you want to do any question, or if you want collaborate with me and with Andrés Prieto in the future. Thank you very much.
Hello. I have prepared a pre-recorded video and it is uploaded to the session platform. I thought this will be played automatically by now. If this is not the case or not like this handled, I just can share my screen and play the video because I prepared it too, right here. And before I start with my short presentation, just a heads up from Professor Bednar, who is the session chair. If any tech moderator is available right now, or anyone knows how to get a moderator, he is the supervisor of the session and wasn't able till now to unmute his microphone and moderate the session till now. So now I will show you my prepared video. All the best, enjoy, and I hear you later.
So this means that he's muted himself.
This is the video.
Yes.
Hello, my name is Sakani and I work at New to our literature review and assessment of the applicability of the Lattice Boltzmann method derived from the influence of convection and question behavior. In the last 2 decades, the Lattice Boltzmann method proved to be a helpful tool for studying the behavior of flows in the mesoscopic domain in a variety of fields, covering a wide range from medicine, geology, to material technologies. Although the method gained popularity in the before-mentioned fields, the applications in building physics have been limited. It was used to evaluate thermal comfort and some general testing and exploration to determine possible fields of application have been done. For example, it could be used to deduct describing parameters like viscosity of a porous medium or to calculate the natural convection in building components. So, first of all, one has to ask, why hasn't there been more involvement in the exploration of this method? One of the driving factors seems to be the simulation domain or scale the Lattice Boltzmann method is usually operating on. Most of the problems we are faced with in building physics take place on a macro scale level. Our usual suspects to answer questions on this domain are hygrothermal simulations when evaluating building components and CFD or network simulators when trying to assess thermal comfort and other questions on the whole building level. While some fields of physics and chemistry concern themselves with operations on the microscale level, like molecular dynamics, the Lattice Boltzmann method usually describe problems in between these on the mesoscale domain. The discrepancy of the problem scale leads to the unavoidable task to find problems in the field of building physics to apply this method to. While for thermal comfort, the Lattice Boltzmann method can be used to replace CFD simulations, and due to its highly parallelizable nature, speed up those simulations in certain situations, especially for hygrothermal simulations and moisture safety, the applicability of the LBM is not of trivial nature. Therefore, in this review and assessment of applicability, we wanted to shed some light on the question if there is a potential of the LBM to have better characterized certain phenomena. Due to the favored simulation scale of the Lattice Boltzmann method, problems which occurred in gaps and joints, like convective moisture transport due to natural convection, seemed like a good fit for a problem domain to apply this method to. An example of such could be the air gaps between EPS board joints and EPS and purlin depicted in this model of a ventilated attic by Lewis et al. Here, potential airflow, either naturally occurring or forced, could lead to unwanted moisture transport in between these layers. After determining the problem domain, we were posing our question on, we narrowed down the literature review to the following subfields, which seem to have subtopics relevant to our question how to couple analysis between a mesoscopic and macroscopic scale. The subtopics include natural convection, porous media, and flow through channels and tunnels. When looking at natural convection, the topics square cavities, porous media, and the coupling of analysis were chosen as potent subtopics in regard of the research question. The square cavity can be regarded as a general reoccurring fitness check for the LBM. The usual model configuration one is presented with is a 2 or sometimes 3-dimensional square cavity, which is differentially heated to induce natural convection of the medium inside. More complex domains involve the addition of obstacles inside the cavity, which can be heated or not. Studying porous media, either the flow through or around the media and the influence of the porous matrix on its behavior is analyzed. Coupled simulations using the finite volume or finite difference methods with the LBM to simulate natural convection could also be found. These hybrid Lattice Boltzmann methods showed speedups in computational performance and lowering of mesh resolutions depending on the coupling techniques. Porous media was chosen as a review topic since most of the materials we are dealing with when analyzing the moisture safety of building components are of porous nature. Especially the deduction of parameters for transport processes show promising coupling possibilities. Souza and Nabovati showed in 2008 that they could deduct the permeability of a porous media model via a LBM simulation. For this, they randomly generated the pore structure, ran a LBM simulation, and based on the results for the speed of the fluid traversing through the medium, were able to recalculate the permeability needed for the Darcy equation to recreate this behavior. If you remember the before mentioned example of gaps in between EPS boards and joints, one cannot ignore the wide range of work done when analyzing the flow through channels. The vast variety of these works are very well suited to be consulted for validation of self-created models and optimal calibration of the Lattice Boltzmann method for different boundary conditions. In the paper, there is also an outline of the different LBM schemes used for the different topics, where this information was available. We also looked at the distribution of papers in regard to our research topics of the last 2 decades. We can see the general increase of work done in the reviewed areas in the last couple of years, but this does not have to necessarily correlate with the research question itself, but may also very well be due to the rising popularity of the Lattice Boltzmann method in the research community. Although we narrowed down our research question to the coupling of the Lattice Boltzmann method with hygrothermal simulations, especially for unwanted moisture transport by convection, a general goal of this review is to provide a good starting and reference point that can be conducted by researchers interested in using the Lattice Boltzmann method in the realm of building physics. Concluding, we can say that we couldn't find any works where the LBM was used in connection to hygrothermal simulations. And in general, the reviewed works show that the LBM is in good agreement with the published data from the reviewed fields, solidifying our hypothesis of the fitness of the Lattice Boltzmann method to be used as a tool in our further research. So what is next for us based on the conclusions we could draw from our review and assessment? For now, the deduction of convection relevant parameters show the most potent possibility, in our opinion, to couple the LBM with HAMS simulations. While as a next step, we will focus on determining a subset of the usable parameters of the macro scale. The goal is to show the applicability of the coupling between the Lattice Boltzmann method and hygrothermal simulations in a numerical model. This should conclude our short overview. I hope I could spark your interest in the Lattice Boltzmann method and its possibilities in the realm of hygrothermal simulations. For now, I'm looking forward to the following presentations and wish you all a nice conference day here at WBC 2022.
All right. And now I'm live. Hello to all of you at WBC live and all to the hybrid guests online. This was my short presentation. As I said, we've focused, in my opinion, on a very interesting topic. This is a start for us in this research area. And this paper should be a general starting point, not just for us, but also, as I said, as a last point, it should be as a general overview for everyone interested in this. And now I see that Professor Bednar has his hand raised. And since he's the moderator, I will just let him do his work if he's hopefully available now.
Now it seems to work. Thank you very much. So now I'm in a different role at the Teams meeting. So a warm welcome from me too. And you already saw two presentations on moisture safety, but the floor is now open to your questions to Andreas Saccani. I'm not sure if anybody's hearing me, but perhaps you can make some sign or some. Can you hear me? Okay, great. Now it works. Perfect. So Lattice Boltzmann method. Andreas, perhaps you can tell us a little bit on your future ideas on using Lattice Boltzmann. I think now Andreas also should be a speaker in the Teams meeting. Otherwise, we cannot hear him. Is there any organizer who is able to put Andreas under the speakers and not under the guests? Yes, Andreas, now perhaps we can, if you unmute yourself. Yes, it works, yeah. Mm-hmm.
I'm back. Please, if you have any questions, just feel free. If you are live or able somewhere in any other way to unmute yourself to interrupt me, or just drop some questions in the chat. This seems always to work. Yes, Professor Bednar, because you asked. So the Lattice Boltzmann method, we are looking in applying it as a tool for convective moisture transport. So, and as a starting point, we will focus the first steps in our research, as I said, in a domain which we think is the best fit for this method, since it is a simulation tool. It is a method that is situated between two domains. The one domain that we are used to use, the macro scale domain, where all the HAM simulations, CFD simulations are usually happening. And these microscale simulations, it is situated in the mesoscale level. So one part of this review was an assessment to find out where we could in our future research apply this method to. And convective moisture transport, especially in between gaps, seems like a good starting point. The end goal is obviously to include it in a bigger numerical model, but as an initial first step, we will look really at this small problem of gaps. We will assess and compare also different tools, beginning from CFD simulations and other hum solvers, which are, for example, applying CFD simulations to look at this problem of gaps. Trying to answer more and more the question that the Lattice Boltzmann method is really fit for research work. And right now, one thing that is in our works, we are in for another conference, a paper is pending where we looked into especially these airflows that I have showed you in the paper in between these gaps at the insulation layer at the EPS boards, where we showed a first numerical approach with the Darcy equation to show that we can predict in a qualitative way the airflow occurring and the convective moisture transport occurring in between these gaps and joints in an EPS board layer in a real attic where we have measurement data.
Yeah, thank you very much. So I think now it's time for the next speaker.
All the best. Bye.
Thank you very much. Now our next speaker is also online, Mr. Tse Chao. He's from National Research Council of Canada, and he's giving us a talk on the effects of air change rate and moisture load related to moisture index and the expected moisture performance of a wall assembly. So I hope some of the organizers can change Mr. Tse Chao to be also a speaker. And yeah, great. Now, Mr. Tse Chao, perhaps you can unmute yourself and give us your presentation. Yes, we can see you already.
Okay.
Thank you very much.
Hello, everyone. So, so I should play the video from my side, I suppose. Okay, 1 second. Let me take a look. Okay, can you see the video, the screen?
Yes, we can see your video.
Okay, just let me know if it has voice, if it has sound. So.
No, I think no, we cannot hear the sound of the video. There's.
So in this case, how can I?
Yeah, there's one. I think there's one button you have to press to get the audio also.
To get the audio, okay. 1 second. Let me take a look.
Perhaps before you start to share your screen, there must be a button. Yeah.
Okay. Including, okay, yeah. Okay, I got it. Yeah. Just 1 second.
Fellow
okay,
at
can you hear it?
University.
Yes.
I'm also a visiting worker working for the National Research Council of Canada. The study I'm going to present today is about the effects of air change rate and moisture load related to moisture index and the expected moisture performance of a wall assembly. The moisture index was developed by the National Research Council of Canada, and it was used to describe the extent of moisture load imposed to wall assemblies located in different regions across Canada. So this index incorporated together with the number of heating degree days for a particular location was used as an indicator to determine the minimum level of moisture protection for exterior walls. When the moisture index is greater than 1, the cladding assembly requires a second plan of protection incorporating a capillary brick and sheath membrane, building elements that can be presented in various forms given the different types of wood frame wall assemblies constructed in practice. As we know, the detrimental effects could occur to wood components of walls, at least when it is exposed to excessive moisture load for a prolonged period of time. Typical effects include mold growth and wood decay. For location with a higher moisture index, the wall has a greater chance to expose to excessive moisture load. The objective of this study is trying to figure out to what extent the moisture index can reflect the performance of walls based under different conditions, particularly the ACH and the moisture load. And specifically, the procedure includes performing hydrothermal simulations for vinyl-clad walls being located in different Canadian cities with different moisture index subjected to different levels of ACH and moisture load. And in the second step, we'll derive the mold growth index for wall assemblies subjected to climate of these cities, and then investigate the correlation between the mold growth index and corresponding moisture index. The simulated wall consists of a layer of vinyl cladding and asphalt impregnated paper-based membrane, an 11 millimeter thick OSB sheathing panel, 140 millimeter insulation, a vapor barrier, and the gypsum board. The depth of the air cavity was set as 2 millimeters to represent the space beneath the vinyl, which varied from 0 to 5 millimeters for an actual constructed vinyl wall. Properties of materials of the wall assembly were obtained from the NRC material property database. Boundary and field conditions for the simulation are shown in this table on the right. The moisture load and the air change rate are the primary variables for this study. So in this study, we implemented the 2 levels of moisture load and 2 levels of ACH. So then thereafter, we will investigate their effects on the extent of correlation between the moisture index and the moisture performance of the wall. One level of moisture load was considered as 1% of the wind-driven rain load, as suggested by the ASHRAE standard 160. And the other level of moisture load was based on the water entry functions obtained from water tightness tests. So this is the specimen that was tested, and it has the same configuration as the model used in the simulation. Okay, so so we have used the climate data for 11 Canadian cities in the simulations, and these cities are located from the west to east coast of Canada, and they have diverse climate characteristics. And also the moisture index for each city are also different. So to permit having a greater number of samples and thus generating more results and a more reliable conclusion, for each city analyzed, 15 sets of 31-year climate data for time period 1986 and 2016 generated from climate model were used. And these sets of data were initially used to generate the future projected climate data. So as you can see here, so on the left is the plot between the average the mold growth index and the moisture index. So the moisture load derived from water entry function and the smaller ACH would result in a greater average value for mold growth index under the same value of moisture index. Also, the climate with a greater moisture index tended to cause greater values for average mold growth index for the wall, having the same level of moisture load and ACH. The correlation coefficient was 0.75 for the vinyl-clad walls and then using 50 ACH, and the moisture load derived from the water entry function. When the moisture load was reduced to 1% of the wind-driven rain load, the correlation coefficient was also reduced to 0.61. At the same time, for 200 ACH, the correlation coefficients were only 0.38 and 0.4, and changes in the moisture load had no significant impact on the coefficient, as the mold growth index did not vary with the increase in moisture index when values of moisture indices were less than 1.2. So it also means that with the given ACH, the moisture performance of the wall sampling was not sensitive to moisture load, represented by the moisture index. And as shown, the plot on the right is showing the correlation between the maximum mold growth index and the moisture index. So for cases using 50 ACH, and moisture load derived from water enrichment functions, the mold growth index were extremely divergent when the moisture index was lower than 0.8. When the moisture index was greater than 0.8, then the maximum mold growth index is convergent at the upper limit. For 200 ACH, values of maximum mold growth indices were relatively small and concentrated for approximative values of moisture indices, as greater values for ACH could remove moisture in the wall at a greater rate, and there was conducive to maintain a dry environment in the wall. So for cases having moisture indices above 1.2, values of maximum mold growth index for the wall subject to 200 ACH and moisture obtained from the water enrichment function become extremely divergent. Okay, from those graphs, so this is an overall summary for those plots. So it is evident that the effect of ACH through correlation is greater than the moisture load for the simulation setups as were implemented. So from this study, we can conclude that the correlation between the two sets of analyzed indices were highly dependent on the moisture load and the ACH levels as implemented. And when the moisture load and ACH were favorable to the humid environment, correlations between the mold growth index and moisture index were higher than those were favorable to a dry environment. And also the future investigations will include the additional levels of ACH and moisture load, and we will also investigate this type of correlations for other types of walls or walls with different configurations. So that will be all. Thank you very much. Any question?
Yeah, thank you very much for your presentation. Is there any question from the audience? Perhaps somebody could raise his hand. Yes, there is a hand. Perhaps you could get a microphone. I cannot hear you, but
no, I can't either.
Perhaps we need some.
Yeah, I think it's on that side is muted. Yeah.
Yes, the organizer is muted. Yeah. Somebody has to unmute the organizer. Yes, now it should work. Yeah. Yes, great. Yeah. Hello.
Okay, all right. Thank you for the presentation. I'm Priya from RMIT University. My question is regarding the air change rates you have assumed for your simulation. For example, 50 ACH and 200 ACH. And I'm just wondering what does actually it mean in the real situation? Is that 200 ACH is a very, very windy scenario?
Yes. So yeah. So the ACH is the air change rate in the wall sampling. So a greater ACH will intend to maintain a dry environment in the wall. So a greater ACH means like the yeah, as I just said, like so it intended to keep a dry environment in the wall. So it will has less chance to the mold growth would occur in the wall. so with a greater SH. And the value of 50 and 200, so there were different studies. They have measured or investigated the value of ACH, and that is the range of the ACH in the vinyl wall assembly as tested in this study. Yeah.
All right. My question is, how this is actually translated into a practical scenario when you have those kind of walls installed for a house, and what would be the natural wind conditions, So is 200 ACH a realistic amount for?
It is well, okay. So for that certain number, it is an average number from it is from a study, and it is an average number from a duration of time. And currently, we are looking into the wind velocity dependent ACH. Yeah, for our study. Yeah.
All right. Thank you very much.
Thanks.
Yeah, thank you very much too. And now we come to our next topic. Just a question to the organizer, Mr. Lewis cannot be here. Are you able to present the video, or shall I play the video? Is there any suggestion? Mr. Jennings, can you play the video, or shall I play the video? Perhaps I can't hear nothing, but so I would try to play the video. So the next presentation will be, or would have been done by Thomas Lewis from TU Wien about the results of a project, a feasibility study on the conversion of historic brick buildings to flats. So I hope you can see the video and hear his voice.
Space for free, a feasibility study on the conversion of historic cellars to living area, to flats in downtown Vienna in Austria. This project was subsidized by the program Stadt der Zukunft, an Austrian national program, City of the Future, managed by the company FFG, with two project partners, the Technical University of Vienna for the Hygrothermal simulations, and the private company Gassner and Partner, which specializes on the refurbishment of old buildings in downtown Vienna. You can see such a building here on the top right. The walls are made from brick, and they have cellars which look frequently like this one here, with moisture content that leads to salt efflorescence. And the goal of the project was to help urban densification, but without having to erect new buildings, without, I will come to that later, without additional heating demand, and of course without running unacceptable moisture risks. The methods we used were hygrothermal simulations and measurements of temperature, moisture, and heat consumption in real cellars converted to flats by the company Gassner and Partner. You can see a typical cross-section, vertical cross-section of such a flat or such a building here, with the cellar that was converted to living area and used flat above. The important applied measures are, of course, the thermal insulation, where it was possible, so the floor and the outer walls, but the outer walls were not accessible everywhere. At the inner courtyard, that is on this side here, the soil level was lowered, giving access to the outer wall, but also making it possible to enlarge these cellar windows to nice large windows that improve the lighting situation. And the last action, or the last important action, was to install a mechanical ventilation plant that allowed to recover the heat and also had an impact on the moisture regime. I will come to that later. But on the outer side, no insulation. That is the street side. No insulation could be applied for economic reasons. So it was not dug down here. So the special aspects are no thermal insulation could be applied to the wall adjacent to the street or facing the street. There was this new mechanical ventilation plant with a special moisture-driven algorithm that compared the moisture outside with the moisture inside. So whenever the moisture content outside was smaller than inside, the absolute moisture content, when it was drier outside in absolute terms, ventilation was well possible. When it's more moist outside, this was the problematic path. We decided to nevertheless run a hygienic air change rate with hygiene reasons prevailing over moisture, mold, and mold formation reasons. And a special moisture tolerant interior plaster was also involved in the project. The first research question regarded the energy, the winter case. Can we use the heat losses of the unrefurbished building of the flat above the cellar to heat the flat in its refurbished state? So can we use these heat losses to entirely heat the new flat without having to supply additional heat? And can we thus have space for free, energetic space for free, which also gave the project its name. The second research question was, how about the moisture? Do we run a risk here? And for two reasons, this is a good question, because we are obviously in the cellar in contact with the surrounding soil that is cold and moist. So the walls and the floor become cold and they may suck water from the soil via capillary action. And we made a sensitivity study in a pre-study on how far this rise of the damp in the wall depends on the water content of the soil. And the second risk attached to this or linked with this is the warm and moist air that in summer enters the flat and gets into contact with the wall and floor surfaces and may condense even there, or may lead to mold formation. Here are the results of these two questions. So first, the energetic question: can we have space for free? According to our simulations, yes, we can. We see in this chart here that shows the energy, the heating energy per square meter in year, the bandwidth of the heat losses in the unrefurbished state, so before refurbishment of the flat above the cellar to the cellar. And then below we see here the heating demand of the new flat in the cellar, so in the refurbished state. And we see that this is way below the losses before refurbishment. That means these losses are sufficient to cover this demand. So it is possible to heat the cellar just with the losses from the top flat. And this result is stable across different set points, heating set points, and different air change rates, even up to a quite unrealistic high air change rate. The second question regarded moisture. Do we run into a moisture risk using a cellar as a living space? So far, according to our results, it does not seem so for this specific case and these specific assumptions. Using a mold formation model, this model is called the Vitanen or VTT model and is based on the so-called mold index that ranges between 0 and 6. Here in our study, the values were so small that our scale range extends only up to 1. We look here at an outer wall and see the values are very, very small. Only from a value of 1 onwards, mold starts to grow and the spores start to germinate. The second aspect were the contributions to moisture inside from different parts. There were three important parts: the so-called interior moisture loads, basically from the users, sweating, breathing, cooking, then the ventilation, and then the building components that are in contact with the soil. And the interesting aspect is that the contributions from the building components are much smaller than the contributions from the user. Moreover, the results are independent of the air change rate, which is quite surprising with regard to the contributions from the building components. There are limitations of the study all regarding the simulation, the data on the material properties, in particular the moisture content of the soil and the moisture behavior of the brick. Furthermore, the geometry was simplified. Even if the software could handle three-dimensional geometry, there was a certain assumption on the user behavior. The mold model so far was validated only in the laboratory, and the exterior climate especially might change in the future towards warmer and more moist summers, which would increase and therefore change the result what regards the moisture risk. Thank you.
Now the floor is open to your questions. Are there any questions? If there are no, I cannot see currently any rising hand. So as it does not make much sense that I ask myself some questions, so feel free to read the paper and send your questions per email to the authors. Now, this was the final presentation in our session. Thank you very much to all of you attending the meeting here, and have a nice day at Melbourne or somewhere else around the globe. Goodbye.